Now let's talk about another concept which called a hardware threading. I hope many of you are familiar with the term threads, and probably some of you have already done some of the parallel programming using threads, using multiprocess, and so on and so forth. So, if you are familiar with the thread concept of thread, it probably would be easier for you to understand. Okay, so but in this case, it is not a software thread as per se; it is a hardware thread. Software threads are maintained and managed by operating system. It is not even related to the hardware. It's an abstraction of the operating system, and operating system manage schedule this thread in a most efficient manner for a given load in the system. Here, load means how many different processes are running, what is their priorities, and so on and so forth. But hardware threading is nothing to do with the software thread. It's a completely internal to the hardware, but the concept is very similar. So basically, let's see what type of problem a hardware threading address. All right. So as I said earlier, we follow in modern computing age, we follow a mixture of von Neumann architecture and Harvard architecture. So von Neumann architecture, according to that, we store all the data and the instruction in the main memory, and then to follow the Harvard architecture, we have some intermediate memory called instruction memory, data memory, where your execution program stores, at least part of them stores, by the way, and part of your data needed for your program execution is stored in the memory. We'll see how the management of these things occurs, what is the performance impact, all in your memory module study. But to understand this concept of hardware threading, all we need to know now at this point that it might happen that the program you are executing on this system are not present or cannot be present in total, in completion. Let's say you have 1000 instruction in your program, maybe let's say 350 are stored in the instruction memory. Maybe for another example, your program is operating on, let's say, 1 gigabyte of data. Okay, they're processing them, but in that 1 gigabyte of data set to be processed, this data memory, in the intermediate data memory contains, let's say, 256 megabyte out of 1 gigabyte. Okay, so what I mean is that this intermediate instruction memory and data memory may not hold your program and your data completely. Okay, it's a partial storage basically. Now that challenge poses a challenge, right? Let's say control unit is operating on your instruction and it's fetching instruction from the instruction memories, it's fetching corresponding data from the data memory, crunching, processing, etc. Now at some point of time, control unit may want to fetch some instruction which is not a part of this intermediate instruction memory. Then what need to be happen? Then the whole system need to be halted, and then the corresponding instructions which is not present in the instruction memory has to be fetched from the main memory first into the instruction memory and then sent to the controller unit. Similar thing will happen for the data memory. If the controller unit fetching some data which is from the data memory, and let's say that data is not present in the data memory, then whole system need to get halted, and then corresponding data need to be pulled out from the main memory, first stored into the data memory, and then sent to the control unit. So if that is the case, then our 5 cycle, remember our 5 cycle execution: instruction fetch, instruction decode, execute, memory, and write back. Now we need to handle this situation, as I described, we need to introduce something like a wait state. Why? Let's say for example, instruction fetch, controller goes into instruction fetch and then requests the memory system, hey, send me the data, send me the instruction. And then instruction memory sees that, well, the instruction you are trying to access is not inside this instruction memory. It need to be brought from the main memory, which, by the way, the main memory access is much slower than your instruction memory access. That means from this instruction fetch, this whole memory system need to tell control unit that, hey, halt, wait a minute, I need to bring those data from the main memory and then I can serve you. Okay, so here the state changes as I try to simplify it a little bit here. We said from the instruction fetch I have two paths, right? So one option is there is no update needed, mean your instruction is in the instruction memory. Then it can go directly, fetch is complete, and you go to the instruction decode and register fetch. But from this instruction fetch state, there may be one point you need an update to your instruction memory. So what it will do then, this machine will go into the instruction wait state. And it will wait there till all the updates are not done. Means it is waiting on this memory to get the next instruction, but this memory is telling the control unit, hey, wait till I'm done. So it is basically checking that status. Okay, update is not done, and it is still staying in the I wait state. And then once your memory, this bringing back from the date instruction from the main memory into the instruction memory and then sent to the control unit, that is whole operation is done, then a flag is up and saying that, hey, update is done, you can take this instruction. Then your processor goes into the instruction decode and register fetch state. All right. Similar thing happens if your execution, after execution phase, there is a load word or stored word kind of instruction to be done, and that part of the data is not in your data memory, then your processor need to go into the data wait state till the memory system updates your data memory, bringing back those corresponding data from the main memory. So clearly we are here incorporating some wait state, and as I said, your main memory is really slow with compared to the processor and control units. This wait is significant. It can be order of 100 or 1000 cycle that you need to wait there. So that means it's going to be an waste of time, because processor as a resource is not doing anything. It's not crunching any value. It's not engaging the ALU. It's not engaging the register file and so on and so forth. It's just idle. So that resource is waste. So point is there that without, okay, so when, not without, when one process gets stalled like this, means it's waiting for the instruction memory update or data memory update, can there be any other process whose instruction and data are present in those instruction and data memory? Can they start? Okay. Assumption, of course, here is we are talking about a system which is running multiple programs in parallel. Okay, multiple programs in parallel or multiple threads in parallel. Here the thread, the term I just said the thread, I mean the software thread. What I mean, that generated by operating system, and you are doing some parallelization of your program. They at that thread level, it process and a thread has some differences, but concept-wise they are basically the similar thing. So assumption here is that we are in a system. Our system is running multiple such programs. So since one program is making the control unit halt, can we somehow like detach that process till it is being waited on the memory? Can I execute another instruction on that same hardware. That's the concept of the hardware threading.